started. So the first thing to note is that so far we have used what we call a rectangular coordinate system for our functions, right? So what that means is we have talked about, taking the plane and breaking it up into rectangles, right? That's the standard. How do we talk about distance and how do we talk about going from one point? We have some point here, x, y, and we know that we think about this as a distance of x from the origin on the x-axis and a height of y on the y-axis. And it turns out that this is not always the best way to do it. And so here in this situation, we often think of y as some function of x. So there's a relationship between, if we have a curve, so curves here are given by y equals f of x, or and we had the idea, the notion of implicit functions, which I'm not going to start diving into again, but we talked about that in Calculus 1 briefly. These are things like equations, like for a circle. And one of the things to keep in mind is this is not always the best way to do it. It's not always ideal. So particularly in applications, like one sort of thing that this kind of one downside to this to using y equals f of x is that it doesn't give a trajectory. Or another way of thinking about that, it doesn't assign direction. Now that might be meaningless to you right now, but let's think about it. If I were to just graph y equals x squared, well, we know that's this parabola. But the way that I define this curve are all the points that I have every x coordinate, and then you square the x coordinate. That's how you get the y coordinate. But that doesn't really give us anything about direction. And what I mean by that is, imagine an object was moving along this curve. How do we know if it's moving this way? How do we know if it's moving this way? So one of the things we'd like to do in order to assign direction so that we can use sort of curves in the plane for applications, again, imagine an object maybe moving around a circle. How do we know if it's going clockwise or counterclockwise? What I mean by that is if I just draw a circle of radius r, this is given by x squared plus y squared equals r squared. How do I know which direction? If I want to describe an object moving around a circle, how do I know which direction it's going? So hopefully you understand that we're missing some information here. So by the way, thank you to the three of you who joined. I feel bad that we had to do it this way, but I wanted to at least offer a class, even though I know most of us don't want to be doing anything today. So one way to do this is to think about a point moving along a curve. So here's the idea. Imagine an object is moving along the curve y equals f of x. So what this means is this means both x and y are functions of, say, time. So x, we would say, depends on t, and y depends on t. Thus, if you want to think about it even more generally, the ordered pair x, y is really dependent on time as well. Does anybody have a question or a comment? I get some water. So what it's useful to do is it's useful to write this as a new function. Say r of t. So r of t is equal to some function of t, comma, some other function of t. So I'll use f for the first coordinate and g for the second coordinate. So again, as we said, you can think of this is your x coordinate, and this is your y coordinate. So we give a name to this. So we call x equals f of t and y equals g of t parametric equations. So now this function r, in the sense of what your definition of a function is, a little more elaborate. Notice there's an input, but the output is not just one number, but an ordered pair. And so this is very closely related to what we call vector valued functions, which you will study if you take Calculus 3. If you've had physics, you might have seen what we call vector valued function. But this is a different type of function than you're used to. The input is a number and the output is an ordered pair. But what this allows us to do is this allows us to give direction. So as we put t in and we think about t starting at, say, 0 and t increasing, that allows us to trace a trajectory. So let's look at an example. We'll go on the next page to do that. So let's say r of t equals t, comma, t squared. And let's say that t ranges between 0 and, say, 2. So the way to think about this is if you draw your XY axis, and we think of this as 1, and then this is 2. And we'll think of this as 4. This is 2. So let's think about what happens if we make a little table like we would have done when we were children learning algebra. When t is 0, we get to 0.00. When t is, say, 1/4, we get to 1/4, 1/16. When t is 1/2, we get to 1/2, 1/4. When t is 1, you get 1, 1. And then, of course, when t is 2, you get 2, 4. And so the way to think about this is as t goes from 0 to 2, you imagine that we are tracing out this curve. So for example, this is the point 1, 1. And this is the point 2, 4. And by doing it this way, we can imagine there's some sort of direction along this curve. And so, of course, this point corresponds to t equals 2. This point corresponds to t equals 1. Now, you might say, what's the intuition for this? Well, the intuition is as follows. If we can abuse notation for a second and just sort of cheat, let's pretend that I can differentiate this thing. So let's pretend for a second that I take the derivative of r. Now, we don't know what this means yet in Calculus 3 to talk about it. But if we were to differentiate this, what's the derivative of each piece? It would be 1, 2t. And so if you think about these things right here, 1, 2t, if you think about this not necessarily as a point, but if you think about it as a vector, and I know many of you don't know what a vector is yet, but if you think about this as a vector at given points, like for example, what is r prime of 0? Well, that would be 1, 0. So if you think of this as a vector, and again, I know most of you don't know what a vector is, these vectors are really the tangent lines. You could think of this as being the tangent line at 0. It goes right 1 and up or down 0. And then, for example, what is r prime at 1? Well, that would be 1, 2. And so what these tangent lines do, if you think of this in terms of physics, so I go to the right 1 and I go up 2. You can make the connection, and some of you may know this from physics already, I'm not quite sure. What do I mean by right 1? I go to the right 1 unit and then I go up 2. And so remember, if we think of the derivative as being the velocity of an object, then we can think about these tangent lines, these vectors, as telling us and if you know anything about, like, and some of you, I know you do show, but I know you guys were doing some of this stuff like angular momentum, and these vectors help us describe the curve. So anyhow, we're not going to get necessarily into that right now, but if you could imagine that, it helps us understand why we might want to describe curves this way. Okay, any comments, questions?
Just to be clear, right? So what we're gonna learn right now, is it gonna be there for the finals or no?
Yeah, you should know how to do this for the final. Yeah. We haven't really
Okay.
showed you anything yet. We haven't showed you any types of problems yet,
Okay.
but we will shortly.
And
Okay.
then
Yeah.
did you receive an email from me? I sent you
Yes,
like
I just haven't
six,
had a
seven
chance to
o'clock.
get to it yet. I'll make sure I get back to you in the next day or so.
Okay,
All
sounds
right.
good. Yep.
Yeah, I apologize, but it's been really hectic here with everything going on. Okay, good. Here's another bonus for these examples is we can also easily describe all types of curves. So suppose now this example, let's take R of t and let's call the first one we'll say is 3 cosine of t, comma 3 sine of t. Now, what is this thing? Well, if you think about these guys in terms of x's and y's, and you make the connection with things you would have learned long ago, but perhaps have forgotten, this creature traces out a circle of radius 3, centered at the origin. So it's a bad circle. So what I should do is delete that and use the built-in circle thing. So this is a circle of radius 3. And again, why is that the case? Why is it a circle of radius 3? We'll pick any point on here, x comma y. And what do you guys know about these points? Well, they satisfy x squared plus y squared equals the radius squared, which is 3, so that's 9. Now plug this in, you get 9 cosine squared plus 9 sine squared is in fact equal to 9. So this is a circle of radius 3. And by the way, we should tell you what t does. T should say, let's start it at 0. And if we say it goes to 2 pi, what that does is it traces it in the counterclockwise direction. And you could verify that for yourself by just plotting points.
So you mean plugging just normal points or after finding the derivative? Or
No, I mean, you could think of the derivative if you wanted, but just plug points. Let t be 0. What happens when you plug t equals 0 in? Here's the point, t equals 0. What happens when t equals, say, pi over 2? Well, pi over 2, you get here. When you plug t equals pi in, you get this point. If you plug t equals 3 pi over 2, you get this point. And of course, you could do all the different ones if you wanted.
okay, so do you plug the values in that RT equals to 3 cos t and
Yes, plug them
3
in.
sin
Plug
t?
0 in. What do you get? Replace t with 0. You get 3 comma
3.
0.
Yeah,
Replace t with pi over 2. You get 0 comma 3.
yeah. Okay.
Does that make sense?
Yeah.
Yeah.
So you're trying to find, you said counterclockwise because it's going upward. So as the value of you increase the number of the value of t, the thing is moving backwards, right?
Right. You can
That's what
imagine
you
an
mean, right?
object moving around the circle in counterclockwise direction this way.
Okay. That's because you are assuming that if when t is 0, it's there, then when t is around 1 or something, it moves up.
Well, no, I'm
That's
just
how you're
assuming
doing.
I start at 0 and move all the way up to 2 pi.
Yeah, that's what I mean. Yeah.
You could go the opposite direction if you wanted. You could start at 0 and reverse, and then it would make you go the other way. mean, the best way for you to see it is not think about it. The best way is for you to write it down. Change your domain from, instead of 0 to 2 pi, think of it as from 0 to negative 2 pi. Go the opposite way. Or start at 2 pi and then go to 0. There's lots of different ways you can do it.
Yeah.
And in fact, there's lots of different ways you could trace a circle. These things are not unique. So what we're telling you right now is all we're giving you is here's a new way to describe curves. We can describe a curve either as a traditional function, but there are some curves that we can't describe as a traditional function, y equals f of x. We can only describe them as an equation up until this point, like a circle. However, now if we create this new thing called parametric equations, we can think of a circle's graph as the graph of a function, namely r of t. Okay, very good. So that is one tool. So again, the purpose of what we were talking about there is, here is a tool. The tool is that we are going to come up with a new way of describing curves that is more sort of not more useful, it's a bad way of saying it, but it allows us to describe more curves than what we learned about when we were children. Okay, now, here are some cool facts about r of t equals f of t comma g of t. So take some arbitrary parametric equations in this new function r. So the first thing is, how do we incorporate derivatives? Well, I'm not going to go through the derivation because it's a little overwhelming and it's a lot of symbols, but using the chain rule, we can sort of figure out how these guys are related. They're related in the following way. So dy dx is given by this formula, g prime of t divided by f prime of t. So this is a version of the chain rule. And then the second cool fact is that the integral from a to b of the square root of f prime of t squared plus g prime of t quantity squared. This integral dt, this is the length of r on the interval t goes between a and b. So you have we can now describe the length of more general curves than we could back in early in the semester. Yes, it is recorded. Yep. So now we're saying that we had an arc length formula back a few chapters ago. That formula was restrictive because it only worked for functions y equals f of x. But now we're saying if you have parametric equations, if you have this new function r, we can now tell you its length using this formula. And the derivation is pretty straightforward, but you know, for the sake of not scaring you with scary symbols, and we've already derived it before. So I'm not going to bore you with those details, but you should know how to use this.
So does that B the length of the curve, right?
Yeah.
Does it have to be between A and B?
No. The T, your parameter T goes between A and B. Notice I'm not using X here, I'm using T. So if you have a curve, I mean, this could be a circle. If I go back to the previous example, I would go from 0 to 2 pi. I can find the length of this, integrate this. I mean,
Okay.
you could do that, plug it in, and I mean, again, this is an old thing. We're just looking at it through a different lens. And again, thinking about it's not the way to do it right now. The way to do it is to pick a function and plug it in and work through the computation. That's the way to do it. Now, if do an arc length problem, if you want to get a feel for this formula up here, why would one care about this formula? Well, you might want to know about tangent lines to parametric curves. And this is exactly what it's telling you. It's telling you that, oh, okay, we can get an idea of how y and x are related, even if I have a parametric equation. So, I mean, there's tons and tons of different questions that you could be asked about this. But everything that you'd be doing here is just a new perspective of an old thing. So it's not like you're learning anything new other than new notation.
I had a question. Could you go back to the previous slide?
Yes.
So over there, right, where you did x squared plus y squared equals to 9 and then 9 cos squared t.
Yeah,
So you wrote that just to confirm, right?
that's
Or you have,
exactly right. That's exactly right. So what I'm saying here is your question to me could be, well, how do I know that this R gives me a circle? And I'm
yeah.
telling you, let's look at the coordinates. Let's look at X and Y. If this is X and this is Y, and I look about what relationship they satisfy this relationship. So I am
Yeah.
confirming that this indeed represents a circle. Does that make sense?
Yeah, so anytime that's not true, then that thing is wrong, right?
Well, again, I mean, if you have to be able to confirm, I'm just doing it. Even look at this example. There's nothing that you can convince you that this is a parabola. But
Yeah.
if you think about it, then ask yourself, okay, maybe you start to see a pattern. For example, if you have a traditional explicit curve, so maybe this will help. So here's another cool fact. Maybe I'll call this cool fact 2. We can always parametrize an explicit curve, or more particularly, an explicit function. So what does an explicit function look like? That is y equals f of x. How do you parametrize it? You say, okay, the x coordinate will just be t, and the y coordinate will always be f of t. So if you want to know how I got the example 2 ago with the parabola, I just did t comma t squared. So you could do this for any explicit function. It's one way to always parametrize.
And you didn't post a slide for the Friday lecture, right?
Did I not post it yet?
No,
Okay, I'll post.
because
No, I
I
didn't
think you
post. We
said
didn't
you
have
had
a class
recorded.
Friday. We didn't do anything.
Okay, because you said that you're going to record and then post it.
Yeah, I know, but then I decided not to. I decided to give you guys just a break because,
Okay.
yeah, I mean, because it didn't work for us to do anything new. I mean, we talked about differential equations. If you guys have questions about specific ones, I'd be happy to help solve them. But it didn't make sense to introduce a new concept that way. So,
So about the differential equation, right? So when you integrate both sides, right? So only one side will have the constant c, right?
well, they can both have it if you wanted, but it doesn't matter because if you only need to write it on one side.
Okay.
Yeah, I mean, because if you have two constants, one on each side, if you move one to the other side, you get a new number. So just call it C again.
And then one thing I was worried about is that in some of my questions, right? The homework you gave us, which was 6 questions, some of them I got C as 0.
That could be fine. Yeah, I didn't get a chance to look at it, so I can't tell you if that's correct or not, but you can absolutely have C equals 0.
Okay.
Yeah.
But I just wanted you to look into it before like the exam so that I can know if I was
Oh,
right.
absolutely. I'll get to it before the end of the week. Yeah.
Okay.
I'll get to it. All right. Very good. So that is one useful tool. The first tool we talked about today is this idea of parametric equations. So here's another useful tool. And this is to introduce new coordinates. So what do we mean by new coordinates? What I mean is if I take your traditional point, x comma y, we know that this guy is given by this coordinate system. Now, what I'm going to do is I'm going to draw a line. I'm going to draw a line from this point to the origin, and I'm going to measure this angle, and I'm going to call it theta. And then I'm also going to note that this line has a length. Its length I'll denote r. So there's a connection between r, theta, and x and y, and this dates back to elementary trigonometry. Note, r is equal to the square root of x squared plus y squared. That is the Pythagorean theorem. Another thing to note is that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. These are basic fundamental definitions in geometry and trigonometry. So what this suggests is instead of describing a point in the plane as left, right, up, and down, we are going to describe it by its distance from the origin and its angle from this x-axis. So if I draw a picture again, we are going to reference this point not by x and y, but we are going to reference this point by r and theta, where theta is this angle and r is this distance. And so we call r and theta polar coordinates. So what is the benefit of this? Why would I say this is a useful tool? Well, there are lots of things that when we use regular, what we call rectangular coordinates, which you learned about, or Cartesian coordinates, things like lines are easy to describe. However, things like circles are not. A circle has an ugly description. It's x squared plus y squared equals r squared. So why are polar coordinates useful? Well, circles have quote unquote simple equations in polar coordinates. For example, r equals a is a circle of radius a centered at the origin. That is the equation of a circle in polar coordinates. Real simple. All the points who are a distance a from the origin. Now, there's some context here. Clearly, a must be positive. It doesn't make any sense if a is negative. Here's a good practice problem for you to do. What's the equation if it's centered at another place or another point? Can you determine that? You have two options. You can look it up. So graphing devices are familiar with this. Let's go to Desmos and I'll show you. If I go to Desmos, not only, it can change. If you see here, we have our rectangular coordinate system, our Cartesian, all these, left, rights, up, and downs. I can change this. If I go here, I can go to polar grid instead of, and now you'll see that we're thinking about points in terms of what circle is it sitting on. And so if I just type r equals 4, I get a circle of radius 4. If I type r equals 2, I get a circle of radius 2. And I can also do much more elaborate curves that would be very difficult to do using x's and y's. For example, there's a famous, well, there's lots of famous curves. Say, for example, I type 3 sine of 2 theta. Now I get this. Hold on one second. Girls. You gotta be quiet. We call this. Hold on one second. So we might want to ask questions like, what is the tangent line to this creature at any point? We might want to know, what is the area contained in this shape? These are questions that we might want to ask questions we might need answers to. And by the way, if I change this number inside, it changes the number of, say, petals of my, some people might call this a polar rose. Okay. Lydia, I'm not honestly. All right. So anyhow, like I was sorry for the interruption. We got kids everywhere here. We got questions that we want to answer. For example, we want to know what is the area of this creature. For example, if I draw this a little more elaborate, I might say, what is this red region's area? Can I use calculus to answer it? Again, I don't know that I can emphasize this enough. This particular curve, it would be I won't say impossible, but can you imagine? First off, it's not the function of anything, because it clearly fails the vertical line test that you would have learned about many years ago in an algebra class. So think about that for a second. All right. So anyhow, does anybody have any comments or questions? All right. So circles aren't the only things that are quote unquote simple in polar coordinates. Calculus, and we could go through this, but it's again, we don't want to stress ourselves out too much with scary notation, but it's something that you can easily have done, given if you learned anything from the beginning of the semester as far as things like Riemann sums are concerned, in volumes and areas, then you can readily deduce some very useful facts. So here's a cool fact. Computing areas using polar coordinates is often easier for certain equations. So what I mean by that is, depending on the curve that you're dealing with, it's oftentimes easier to describe it using polar coordinates, and then computing area turns out to sometimes not be as bad. So here we go. So consider a region, we'll call it R for the sake of it. And it's bounded by, let's say, two polar curves. We'll call the first one f of theta, and we'll call the second one g of theta. And we have to restrict where theta goes, so perhaps we say theta is stuck between 2 points. I don't want to use A and B, because that we use that for not when we're thinking about an interval. And since here theta is measuring angles, we use these Greek letters alpha and beta. So what would a region like this look like? Well, a region like this would be, you take two polar curves. So we'll call, one might look like this. So we'll call this R equals f of theta. And then maybe it has another boundary. We'll use a different blue. Maybe it looks like this. Well, that's not the different blue. Use the same one. So here's our polar region. We'll call this R equals g of theta. And then we're stuck between two angles. So how do we represent that? Well, we can think of those as lines that go down to the origin. So let's say here's one. Let's see, here's one. So let me be very clear that this is the origin. So, you know, this angle right here would be your alpha, and then this big one would be your beta. And so the question is, or the region R is going to be this pink shaded region. And so it turns out there's a very simple formula for this. The area is the integral from alpha to beta of, well, what's the area of a circle? The area of a circle
Pi r squared.
Yeah, right. So, but let's think about what this would be, though. Let's, you have to think about the formula. You know that the radius squared is going to be involved. So it doesn't, you don't want to, we would imagine that if we went through the Riemann sum, if we take the f and we square it, I guess, well, hold on, I have it backwards. If we imagine chopping this thing up into little regions, what you end up having is you have g squared of theta minus f squared of theta d theta. Now, here's the thing. It's not pi r squared. Remember, that's the area of a circle. But what about a segment? So there's this 1/2 factor that comes in front. So you might say, huh? Where does that 1/2 come from? Well, we're going to go to remind you what the area of a sector is of a circle. So where does this 1/2 come from? Let me remind you of something you probably learned years ago and since have forgotten. But the area of a segment of a circle if you look at this picture here, you'll notice the area of this sector is half the angle times the radius squared. And so the 1/2 comes from this particular formula. So if you would chop up your region and use Riemann sums, what you'd get is you'd be using this piece. And so that is where the 1/2 comes from. And by the way, a great exercise for you would be to, try to derive this formula. Not saying it's easy, but it's a great exercise on a solid understanding of calculus, because what you're actually doing is you'd be chopping up this region here, and you're going to approximate it by small little arcs. And so, of course, you can use that, the sector of a circle formula, and then you can sum them all up and take a limit, and you get this formula. Now, we can also do derivatives in polar coordinates, but it becomes a little more complicated. And it's a really sort of scary application of the chain rule. And I only say scary, and I don't, for students in Calc 2, but just because your comfortability level with the chain rule is limited, and it's often scarier, to do it. And perhaps instead of writing down the formula, the best way to do it is to ask you to do a problem. So what textbooks normally do, and I'm sure ours does it. In fact, I know they do because everybody does. They just write down this formula, which turns out to just be a little more overwhelming than it is useful. So one of a good exercises, and I'll probably assign this for practice, or maybe your last homework, and that is, uh, given a polar equation, can you find the tangent lines and how you might reason it? Once again, it's a scary thing, but you might be able to reason it. So my feeling for students in Calc 2 is the following. Calculus, or excuse me, integration in polar coordinates is what I've experienced in the past. As you guys grasp it fairly quickly. It's not terribly difficult because you're really just replacing old letters with new letters. But taking derivatives and finding tangent lines in polar coordinates often gives students quite a bit of a headache. Does anybody have a comment or a question? Comments? So what I'll do is I'll probably assign some problems on this, and I'm not, look, I know, look, at some point, here's the downside to a pretty heavy class like Calculus 2 is you guys get worked up because the things we learn on the last day you get tested on within a week, and that's just the nature of it. I wish there was another way, but there's not. You should be able to do this. So the question is before I give you the test, I'm going to give you an assignment, and this assignment it's basically a way for you to get points. So make sure you do it. But it's also important that you look at the problems because those are the types of problems with this stuff that you should be able to do that are part of the Calculus 2 learning objectives. Look, don't forget, one of the reasons I give you a take-home exam is for that reason. It's that I understand it's a lot to learn in a short period of time, but it is what it is. That's the same when you're taking calculus anywhere. You are learning a lot of stuff in a short period of time. It's not always fair. It's not always the ideal situation, but it is what it is. And so my point today was to give you a brief overview of this. What often happens is this stuff is rushed in at the end of the semester. It happens every semester. It's not just you guys. So again, please look at the next assignment, ask questions about it. I'd be happy to write Zoom solutions and have office hours next week. I'd be really, I'm completely happy doing that. So, but I can't do it unless you ask me to do it. So, any other comments or questions?
But can you make sure that you post the solutions of the assignment you give us like after a day or 2 days?
I mean, I can try. I just don't know that I'll have enough. I mean, if I have time for sure, but it's I don't always have time. Believe it or not, it's actually time consuming to do that. And of course, what's actually easier for me is if you tell me what problems, what you did is the right idea, show, but you sent me an email, and like I said, I'll get to it. I didn't have any time yesterday, so I'll probably get to it tonight or no later than Friday, and then I'll get back to you. My advice is, I'll be pretty open next week, so I'm happy to meet if you just want to, and I'm also happy to answer questions. I mean, as some of you have asked me questions and I've given you responses via email, but I'm also happy to get on a Zoom and show you things live, as they say. So, I mean, look, if you look at our homework throughout the semester, there are very few problems that I asked you to do for homework that we haven't done in class. I mean, we did almost everything. And if there's a problem you're not sure of the solution, I'm happy to answer it. You just got to let me know which one. Does that answer your question? I mean,
yeah, it does.
Yeah, in an ideal world, show, but I'd love to write up good, long, in-depth solutions, but sometimes that's just impossible. But again, if we can, if you tell me specific problems, I'm happy to get it out to you. And by the
Okay,
way,
sounds good.
yeah. So what I would tell you right now is, I know you might say about today, well, we didn't do any examples really. That's true, but the kind of problems that I'm going to ask you to solve, or I could ask you to solve, you in these topics, you'll see on the next assignment. So does that make sense? And of course, you can ask questions. I'm happy to answer them.
And will we be continuing the same topic for calculus 3 or no?
Yeah. So Calc 3, you usually start out with vectors. And then
Okay.
what you'll start to do early is you'll make a connection between, if I go back here, you'll make a connection between these ideas of parametric equations and what we call vector valued functions.
Okay.
So Calculus 3 is a really cool course. What you're doing is you're going to take these ideas of derivatives and integrals, and instead of being only worried about one variable, say x or t, you're going to generalize it to multiple variables, say x's and y's and z's. And that allows us to study problems in more than one dimension. So essentially, Calc 3 is you redo the stuff that you did in Calc 1 and 2, but you do it in more than one variable. And
Okay.
then differential equations class, we spend a lot of time studying differential equations. So there's a heck of a lot more to say about differential equations than we said last week. There's a ton more. And we're going to show you how you study them in the modern times, in the classical ways. It's a really good class. So if anybody needs a math credit or science credit, I'd encourage taking that. It's a good class.
Well, I'll be able. Do you think that it will be reasonable to do both of them at the same time, right?
Oh, right. I mean, you have to. You don't really have a choice. Yeah, I
Okay.
think it's reasonable. Most students do.
Yeah, I just wanted to make sure that I'll be able to manage that. And if you think so, then okay.
Yeah,
I
absolutely.
will
And you're not the only one that will be taking both. Lots of students will.
okay.
Yeah. All right. Anything else while I'm here? Someone's chopping it up. Chopping it up in the chat. Oh, yeah, Cammy, I got you. Not a problem. I'll communicate with her. And I don't know if actually, if I can't, then I'll communicate with you. Yeah. But yeah, if you talk to her, tell her not to worry about that. I figured as much. Any other questions, comments? All right. Well, listen, please don't hesitate to email me, Show, but I know you already have, so that's good. And I will tell you, if I don't respond now, obviously tomorrow's a holiday, so don't be going crazy if I don't respond tomorrow. But if you send an email and I don't respond by Friday, just send it again. All right. And we want to make sure that you guys know where you stand grade-wise going into next week. I hope to have all your grades updated before the end of this weekend. And so if you do not be afraid or hesitant to email me and remind me. I know a few of you have, and some of you I've updated and others I haven't got to yet. So again, don't be mad at me. Just continue to email me and annoy me, because I have already annoyed you. And for that, I apologize.
And
Anyhow,
you'll be posting the lecture today, right?
my plan is to do that. I have a couple meetings coming up, but I hope to do that before the end of the day.
Okay.
Feel free to blow my email up about that too, in case I forget, Show. Because here's
Yeah,
the problem. Once
definitely.
I'm done, it takes a while to process on Zoom. So then I have to go download it from the cloud later, and then I have to upload it. So it's not an instant process. It takes time. And so usually, if from the time this ends to the time it's available for me to upload, it takes some time, and it also things happen in between. So, all right.
Yep.
Anything else? All right. Well, someone else. I like it to get the chat on. Yeah, you as well, Mr. Bo. Hey guys, seriously, I appreciate it. I hope you learned something this semester. I hope it wasn't terrible. I know this stuff is hard. I understand. I empathize. I sympathize. You've heard me say it before. There will be curves. Yeah, the tests will be hard. There is a lot of work in this class, and don't forget, this is a 4-credit class. So you're like, oh my God, he said he's going to assign us another assignment. I don't know what you want me to do. I mean, this is it. We got to get you practice. We got to give you practice of what you guys need. So, you know, think of it as practice, not as pain. Anyhow, thank you guys very much. I will look forward to hopefully hearing from you guys next week. And please reach out if you need anything. And have a good holiday. Be safe. And I will talk to you soon. Thanks, guys.